Okay, so now I want to drive through entanglement breaking channel. And so what you need to know about is like what we will be using is the classical message from Alice, the quantum entries from Alice, and what quantum stuff can recuperate Bob. So X1, X2 is just the classical message from Alice, you know. So suppose like this could be 0 or this 1, for example. And so after x1, x2 can be like 0, 1 or 1, 0. And so after you have like a1, a2 that are um, uh, yeah, let's see, you have like the choice between 0 of 1 here, and here's the choice between a and b. And so the messages, can be like 0a or 0b or 1a or 1b or in the other sense. And so well, maybe to be more to not have mistakes, like we can like call it like 2 or 3, maybe. Like maybe it's better like so 0, 1, 0, 2, 1, 2, 1, 3. And so suppose like we have now a1, a2, that's just the quantum entries of Alice. And so after we have the entangled breaking channel, so say take a1 for example, and so after it becomes b1, and here it's the second channels, and after Bob receives like b2, transform it in b2. So yeah, b1 and b2 are just what Bob receive from the channel, and so b1 b2 is just like the combination of the systems depending on what goes out of the channel. So so that's about our variables, and so when you will be writing x1, x2, b1, b2, it just measures like how many things Bob can learn from the messages, classical matrices of X. You have the system X of Alice here, and you want to know like how many things like she will be learning from it thanks to the quantum state that Alice was prepared about it. So yeah, X1, X2 is just the total information injected by Alice at the beginning, and B1, B2 is the total quantum system received by Bob. Whereas little index just signifies a contemporary distribution that we use to calculate this mutual information. Because we first our probability or contemporary distribution like to be independent, like we have like c1 c equals c1 over c2, then it just means that when we write x1, x2, b1, b2 of c, it's just equal to ax1, b1, c1 plus ax2, b2 of c2. So Alice just prepares a1 regarding x1 without occupying herself of x2, and Alice prepare a2 depending on x2 without occupying herself of x1. So what Bob learned from x1 by measuring b1 has nothing related with what he learned from x2 by measuring b2. The two information, the combination of this information just addition together, because the channels, each works on their side alone. So at the end, it's just an addition. And so the fact is, if you calculate the Oliver information, you know that the maximum of it, like it's a max of any random state we can have, you know, it's maximum state, like maximum information we can have. So if you take like a really, really, really big integral state, it can be at least in the better case equal or inferior to this Oliver information. And so as we see, like because the two channels act separately, then we can have additivity about it. And so we just have equality. So yeah, that's the first part of the demonstration. That is always true, by the way. So yeah, for now we just process. That's the easy part. And so in the next, we will need to prove the other sense. So this way we have the equality because we will have find the other sense, which is this one. So that will be the purpose of the next video. It will be just to prove this.